thanks to the organizer for having given me the opportunity to speak at this very nice conference about the recent development that we have been doing in applying DMRG to molecular quantum chemical problems. The title is mostly focused on time-dependent DMRG, so molecular quantum dynamics, but I will start, let's say, taking a step back and also present some work we have been doing in connection to applying DMRG to vibrational structure problem, to the study of time-independent vibrational wave functions in molecules. And this is the first two, let's say, DMRG variants that are listed here. And I will then move to the main part, which is connected to molecular quantum dynamics, to then finally give you some brief notes about a method that we recently introduced in order to go in the direction of explicitly correlated DMRG based on the transcorrelated Hamiltonian approach. And so starting from the first part, so vibrational problems, let me highlight what I mean by vibrational problems. I mean solving the vibrational Schrödinger equation within the Born-Oppenheimer approximation, which means determining vibrational wave functions and energies of molecular problems, of molecular systems, including anharmonic coupling. So by including in the potential energy surface coupling terms, which couple the different vibrations. And here the main differences, like conceptual difference compared to electronic structure calculations, are there. Of course, vibrations are not anymore treated as fermion, but as bosons. So we needed to generalize kind of DMRG to more general kind of particles. And most importantly, the potential that couples the vibration is not limited to the two-body pairwise interaction term, as it would be, for instance, in the Coulomb interaction, but includes higher order coupling terms. And we designed kind of a DMRG variant to study this kind of Hamiltonians based on the MPS-MPO formulation of DMRG. And specifically, we designed two variants of what we call the Vibrational Density Matrix Renormalization Group. The first one, which is kind of based on the canonical quantization, so on the harmonic oscillator second quantization operators. And this is like the natural entry point because it kind of the initial entry point to study molecular vibration, but it kind of implicitly relies on the harmonic approximation, both for the potential expansion and for the reference basis function. And this is not the optimal reference for strongly anharmonic systems, which are the one we eventually want to target. And for this reason, we extended it to this more general second quantization form, which was originally introduced for vibrational coupled cluster, which relies on a completely general potential energy operator and basis function. So in this way, we could also rely on basis functions, which are not necessarily the harmonic oscillator eigenfunctions, but can also be more refined. And however, so in both cases, the DMRG lattice it's composed now of, it's multi-component in the sense that sites belong to different modes, which are distinguishable objects. But besides that, there is also a technical problem related to the fact that the ground state is much less interesting, in a sense, for vibrational structure calculation than in electronic structure calculation, because any simulation of, let's say, vibrational spectra, vibrational properties often involves the calculation of excited states and possibly many excited states. And our first approach to solve this problem was to apply the so-called shift and invert technique to map the Hamiltonian to an auxiliary operator, where the ground state is now the excited state, which is closest to a shift parameter that we use to map the Hamiltonian. This was already employed in DMRG, and I just put here two examples. And it's very efficient to optimize low-lying excited state, but going high in energy, this becomes less and less efficient, mainly for two reasons. First, it's difficult to choose the shift to target the state I'm interested in. And second of all, what we are doing is projecting the eigenvalue equation onto a given site and then shift and inverting it. but it would be better to ensure variationality to do it, like to do those two things in a reverse order. So map the MPO before projecting it into onto the given site problem. And to solve those two problems, we designed first what we call the maximum overlap variant of the MRG, which makes the choice of the shift less important because it chooses the route to follow during the DMRG optimization based on the maximum overlap criteria. So this is kind of the parallel for the MRG of the maximum overlap method used in R3FOC and DFT. And regarding the second problem, we employed a different operator, which is the folded operator, which avoided the inverting the Hamiltonian, which is the difficult step to do it at the MPO level. And the advantage of this operator is that it can be rather easily done at the MPO level, but it leads to complicated operators that need to be tamed and kind of reduced in order to make it manageable. But nevertheless, this folded variant of the MRG turns out being much more reliable than the shift and invert one if we go very high in energy. So this is an example, is the OH stretching mode of a dipeptide. So this excited state is sitting on a very, very high densely populated energy region. And we clearly see the difference in stability between those two DMRG variants. And we can then apply all of that also to calculation spectral properties. So here is the example of absorption spectra, where we properly include an harmonicity also in the intensity, so in the calculation of transition properties. At this point, we kind of took a step back and decided to ask ourselves, but can we treat molecular vibration from a, let's say, more fundamental perspective without invoking the Born-Oppenheimer approximation, because this is what leads to very possibly complicated potential energy operators. And this is trying to study and calculate molecular energies and properties without invoking the Born-Oppenheimer approximation is, let's say, is the subject of study of so-called pre-Born-Oppenheimer methods, which are mainly divided in two classes. The first one being explicitly correlated theories, which are in principle very accurate, but their scaling makes them basically not applicable to systems with more than a few particles. And on the other hand, there are orbital-based methods, which have been pioneered by the group of Professor Anders Schiffer, which basically uses and rely on orbital theory both to describe nuclei and electrons. And as you see here, there have been basically many of the electronic structure methods that have been generalized to this nuclear electron framework. But the kind of, even though it's not clear how relevant are correlation effects in these pre-Born-Oppenheimer Hamiltonians, multi-reference methods were much less studied than the single reference one. And so with the MRG, we thought that this could kind of fill the gap between those two extremes and provide a way to calculate accurate vibrational properties beyond the Born-Oppenheimer approximation for decently large molecules. And all in all, the problem is not much different than the electronic structure one. The main difference being that now the Coulomb interactions are all pairwise interaction, because we are not fixing the nuclei, but we are describing them with their respective wave function. And the Hamiltonian can still be expressed in second quantization, but now we have a multi-component DMRG lattice, because we have both fermionics and bosonic degrees of freedom. So combining kind of the know-how in vibrational electronic structure, we designed and applied the MRG to calculate the ground state of this Hamiltonian. And we had to complement it with a way to kind of construct our own atomic basis, even though atomic is not the proper term since the nuclei are not localized, but let's say our primitive orbital basis to then do the MRG on top. And so we designed a stochastic way to construct this orbital basis, which we call NEAP, which stands for nuclear electron or particle, and combined it with the MRG. And even though this was kind of, let's say, naive implementation in a sense, a pilot implementation, we saw that for a system which is large in the pre-Born-Oppenheimer context, a molecular system as pH3, we were able, thanks to the TD-DMRG theory, which is the purple line here, to go below reference state-of-the-art results obtained with single reference approaches. I should say that we are currently working on, making refining the orbital optimization strategies to push the limits of this calculation even further. And now let's move to the main core of the presentation and apply the DMRG to molecular quantum dynamics. Of course, time-dependent DMRG, applying DMRG to time-dependent processes has been basically a field of research for more than 20 years, and there are many variants that can extend DMRG to the time domain. And the common limitation of any DMRG variant is that the MPS representation becomes less and less accurate as the propagation evolves, and so capturing long-time effects may be challenging. And so our goal here was to see how much this affects the accuracy when we apply the TD-DMRG to molecular problems. And among the different variants of DMRG that have been proposed, we rely on the tangent space TD-DMRG theory, mainly for two reasons: because it's numerically stable, and so it supports large time steps and so long propagations, and also relies on the MPS MPO formulation, which is like the pillar of our, let's say, quantum chemical DMRG frameworks and also code. And in a nutshell, I just want to recall how this tangent space DMRG works, and it integrates the time-dependent Schrödinger equation projected onto the manifold of the MPS with a given bond dimension. And the key idea and the key advantage is that the propagation can be simulated with a iterative propagation algorithm, which is equivalent to the iterative optimizations that we have in standard time-independent DMRG. Let me just jump to some applications. The first problem we targeted were vibronic dynamics, so coupled vibrational electronic dynamics. And let me stress that here by coupled vibrational electronic, I don't mean it in the sense of pre-Born-Oppenheimer that I've shown before, because the electronic degrees of freedom, we describe them not from a full many-body perspective, but just by projecting the electronic degrees of freedom on a small finite set of time-independent electronic states. So, for example, if we consider ethylene, we don't describe the electronic contribution to the wave function as a many-body wave function, but just as a coherent superposition of here, for instance, the S0 and S1 states. And on top of that, we add vibrational coordinates and build a vibronic Hamiltonian that describes the dynamics of the molecule of the combined electron dynamics molecular of the molecules. And all the complexity lies in the coupling term that couples, again, the electronic and the vibrational degrees of freedom. And so we started with a relatively simple excitonic Hamiltonian, where this coupling is described only at the first order term. So this means that the relevance of long-range interactions is rather limited. And so at least from a time-independent perspective, this would be an ideal target for DMRG. And as a test system, we use this molecular aggregate, which we approximated, of course, with the excitonic approximation, but still the resulting vibronic Hamiltonian includes more than 70 degrees of freedom. So it's challenging and can be targeted mainly with the multi-layer extension of MCDDH among the state-of-the-art approaches. And here are some results regarding absorption spectra. And as you see, the convergence of absorption spectra is rather fast with the bond dimension. And this is and the absorption spectra are calculated by Fourier transforming the time-independent autocorrelation function. And this is, again, probably the effect of the fact that the vibronic Hamiltonian has simple interaction terms, and also that those quantities are obtained as, let's say, average over the propagation. And the contribution that gives the spectrum is basically the short time part of the propagation, which is efficiently described by DMRG. And this is kind of confirmed if we look at, let's say, instantaneous snapshot of quantities as the population. So here what we are monitoring is how, when we excite one molecule in the aggregate, how the excitation is propagating through the aggregate. And as you see here, the convergence of this quantity, so the population of the first and last molecule of the aggregate, does not converge as fast and requires a larger bond dimension, which is still, let's say, small compared to basically to time independent, for example, electronic structure DMRG calculation. But since we, let's say, trying to exploit the effort in building kind of a general DMRG tool that can target both vibrations and electronic degrees of freedom, we applied the very same algorithm also to pure electronic dynamics, now from a true many-body perspective, in a sense that we propagate the electronic wave function with the second quantization form of the exact non-relativistic electronic Hamiltonian. And so this kind of leads to the real-time counterpart of DMRG, which kind of complements all the research that has been recently done in extending many electronic structure methods to the real time. And the two most interesting applications of the resulting algorithm are, of course, the simulation of ultrafast processes, which are intrinsically non-equilibrium, but also the simulation of spectroscopic observables, which can be calculated also with linear response theory, but here can be targeted, let's say, by passing the linear response approximation. And again, to benchmark our model, we calculated the absorption spectrum, again, by autocorrelation function of conjugated of the decasine, where we had reference data obtained with TD full CI. And as you see, we can reproduce the reference data, but we can go higher in active space because we went up to 25 electron, 25 orbitals, and reproduce better also the high energy tail of the spectrum, which is where simulating the spectrum from a time-dependent perspective is maximally advantaged, because optimizing such high energy states may become very cumbersome. And as you see, the convergence with M is lower than conventional DMRG, but most of the difference in the last, let's say, increase of M is kind of a vertical shift of all the energy. So this kind of suggests that still TD-DMRG can offer an alternative route to simulate molecular spectra. And it's interesting to monitor and compare spectra calculated with TD and TE, time-independent DMRG. And the convergence of the spectrum with time-dependent DMRG is lower, because we need at least M equal 500 to get the results that with TD-DMRG were obtained with a bond dimension of 250. But still, this is a kind of a good compromise, considering that TD-DMRG can get spectra, let's say, in one shot. And moving to real, let's say, non-equilibrium processes, we simulated also the ionization dynamics of a molecule, so of benzene. And the experiment we are simulating is the one where we kind of instantaneously eject one electron from the lowest pi orbitals of benzene and monitor how the charge kind of rearranges over time. And qualitatively, what happens is that the hole that we create in these pi orbitals get populated by the two upper-lying pi orbitals, and there is a charge migration which oscillates, which keeps going, but of course in the experiment will be kind of killed by vibrational effects, which we neglect here. And even though basically a simple, let's say, 6-orbital picture can explain the qualitative what's happening here, we show, I mean, the simulation showed that actually one must go pretty high in active space in order to convert the oscillation period of this charge migration. And I should stress here that we neglect the orbital relaxation effects, which could, if included, basically make smaller active space sufficient. But going from a CAS of 8.8, which would be the qualitatively good active space, to CAS 2020 leads to a increase of the oscillation time by more than 100 attoseconds. So the electronic structure component of this phenomenon is not that trivial to simulate. And of course, here again, we are neglecting a lot of things like the details of the molecular ionization, those vibrational effects. So the existing difference compared to experiment would probably be it's probably due to this neglect. And what's interesting is that one can also use entanglement-based quantities, and here the single orbital entropy, to monitor basically why we need to increase this active space to get converged oscillation periods. Here I'm representing the entanglement as a function of time of the various orbitals. And what we see is that going from 1414 to 2020, the two orbitals that we are adding are have an entanglement which is larger than 0.2. Here the image is a bit skewed, but let's say the maximum falls above this threshold, which kind of tells and kind of pinpoints the fact that those are the orbitals responsible for the increase of the oscillation time, and also then kind of matter in the basically electron dynamics process. And in the last few minutes, let me move to the last part of the talk, which has to do with transcorrelated DMRG, so explicitly correlated variants of DMRG. This may seem unrelated to what I've spoken so far, but actually we use the imaginary time variants of the TD-DMRG theory I've spoken about before. And so this is the link between those two subjects. And the transcorrelated approach is a very old idea and amounts of expressing the wave function as a CI wave function, which in our case will be the DMRG wave function, and scale it by a correlator. So either a Gutzwiller correlator, which has been already introduced in the previous talks, or a just row factor in real space. And the idea is that the correlator kind of takes care of the short range structure of the wave function, at least in real space, so that the CI wave function, which in our case will be the DMRG one, has to take care of the long range strong correlation effects. And the idea behind the transcorrelated approach is to revolve the correlator into the Hamiltonian to similarity transform it. And this has been recently, there has been a lot of work in this direction by the group of Ali Alavi, where they applied basically the same idea with full CIQMC. And the main problem is that the resulting Hamiltonian will turn out being non-Hermitian. So the variational optimization can be very challenging, as has been already pointed out in previous talk during this conference. But what it has been shown in these works based on full CIQMC is that imaginary time evolution does not suffer from this problem, basically because it doesn't have to calculate both bra and cat, but just calculates the cat. And so it works as well. It was, let's say, as good for an Hermitian Hamiltonian as it does for Hermitian ones. So combining imaginary time evolution, non-Hermitian Hamiltonian is what we call transcorrelated DMRG. And the first playground we applied this theory is the two-dimensional Hubbard model as an example of strongly correlated system, which we transcorrelate in momentum space. And we do that because what has been shown with full CIQMC is that transcorrelating in momentum space is the way to go to make the wave function, let's say, more compact. So we want to see here if the same happens with DMRG. And this is the expression of the momentum space to the Hubbard model. And you see that there is a three-body coupling term, which will become, as I will just explain in a second, the main problem of applying this thing to DMRG. And just some final results, as you see here, if we apply DMRG to the transcorrelated Hamiltonian and combine this with an optimized orbital sorting obtained with the feeder sorting, the convergence of DMRG is in fact much faster with the bond dimension, because we can get with m equal 500 basically a converged energy which could not be obtained with standard DMRG with m equal 2000. And also looking at the entropy structure of the wave function, this confirms, if you look here, that this faster M convergence is kind of due to the fact that the entanglement structure of the wave function regularizes, and so we can encode the wave function as a more compact MPS. And just, we extended this also to larger systems. Our final goal will be molecules, but we already see here that the main problem is this three-body term, which so far we are treating naively in the sense that we encode it exactly. But we believe that we could kind of try to compress it without compromising accuracy, since at the end of the day, the final wave function is a compact MPS. So before concluding the presentation, let me just point out the code that we use for doing all of this, that we call QCMakis. We have now a GitHub repository where you can clone and try it out. So far, it's mostly focused on electronic structure, time-independent calculation, but hopefully all the things that we've spoken about today will come in the near future. And this concludes my presentation. I would like to thank, of course, all the Ryan Research Group, and in particular, Stefan, who will speak later today, and Leon, for which are the main responsible for, let's say, the QCMakis side of the development, and also, let's say, the QCMakis team of our group at ATH. And of course, you for your attention.